Okay. Hello, everybody. Thanks for joining our webinar today. So you're here at the Linac Technologies, Linac Simulators in Action monthly webinar, and this is our March session. So like I said, thanks again for everybody joining. And I'm just going to give everybody a minute or two before I get started. So we had just about 150 registrants of this webinar this month, so that's very exciting. So thank you guys all for supporting the webinar, and I'm glad we can supply a topic that seems to be interesting to you. So hopefully we can keep up with these types of topics, and please, feel free to reach out anytime, and we can discuss our simulators and we can discuss topics you'd like to see in future webinars. Okay, so I'll just kind of talk a little bit as we let some people trickle in. So obviously today's topic is PDD dosimetry. And specifically, we're going to look at how our PDD changes when changing different beam parameters. And we're going to look at, changing our energy, changing our field size. We're going to look at some flattening filter free, and we're going to do some SSD changes as well. And so throughout the webinar, we're going to be using our Linac simulators to explore these concepts interactively. And really today, the goal is twofold. I want to walk through the physics behind PDD curves and give you some PDD dosimetry education. We do a little session on that. And then second, I really want to just highlight how easily these concepts can be taught and explored using our simulation platform or using SIMAC, using our simulators. And at the end of the session, I'm also briefly just going to show you how you can get access to our simulators as well. So I'm just going to show you some just kind of go a little overview of our products, just that it's a little bit clearer. Okay, so as we get started here, I just want to remind everybody there is a free access tier on Linac.ca that gives you 5 simulated beams per day. So if you have an account or you'd like to follow along, log in, sign up, and you can even kind of do some of the beams that we're going to run today in the demonstration. Okay, so that's enough. I think we gave everybody some time to trickle in. So we'll kind of get started now. And if you have any questions as we go, please feel free to just go ahead and interrupt. I think I've given you guys the ability to put your microphones on, or just put it in the chat. I have Karen Ann here who works with Linac. She's our customer analyst, and she can help answer any questions as well. And that being said, I did ask for anybody to put some questions or comments on the registration form so that I could kind of cover it during our webinar. And so here are some of the questions and comments we got in our registration. So I just want to cover them quickly, and then we'll just kind of go back and forth between them throughout the webinar. So we were asked about price information. So I am going to cover our pricing very quickly at the end because we were asked about it. We were asked about small field dosimetry. We'll plan to do that in a future webinar. We don't have small field dosimetry in our simulators yet, but that is coming in the future. We have plans for it. Dosimetry, we were asked about dosimetry demonstrations. So obviously we're doing that now. We're going to look at some dosimetry today. And we have this question, how does increasing photon beam energy affect the PDD curve? And again, we're going to be doing that right now. That's exactly what this webinar is covering. Differences in detectors used. No plans, but I'll now take that into note that that's a topic of interest for the future. And same with cross dosimetry. We have no plans, but I will take this as feedback for possible future webinars or things that people are looking for. We were asked about skills needed to take our courses. Again, I'm going to cover that very, very quickly at the end. Machine calibration was asked about. That's kind of what we're doing. Oh, I apologize. That's not what we're covering today. We're doing PDD dosimetry, but I do have a TG51 workshop available, and we have a TG51 simulator, and so that's definitely going to be in the future, and that's something you can reach out. And I'm gonna explain that a bit at the end as well. We were asked about SRS and SBRT plan evaluation. We have no real plans for that, but again, I'll take that as good feedback of something people are looking for. And bending magnet and flattening filter, that's something we definitely can do in the future, and we have the ability. So I'll take that as great feedback, and I will see what kind of webinar I can do in the future, looking at our bending magnet and flattening filters. Okay, so this is good. But that's pretty much what I wanted to cover before we really get into the demonstration. So let's get over to the platform now. So I'm going to take us to the platform, and really where I want to start is before jumping straight into the simulations, I just kind of want to imagine we're approaching this topic as somebody who doesn't know it, learning it for the very first time. And I just kind of want to show how our platform kind of facilitates that. So, in a classroom setting, we might have an instructor kind of assign some readings to do and some labs to do, but if we're on our own, where we really want to start is our student resource portal. And so our student resource portal, it's found, sorry, I have this tab from the video is in my way. So where we can find the student resource portal is we click our username in the top right. My drop down looks a little different because I'm an admin, but basically we find this student resources here. And this is going to be our starting place. If you never know what to do on the platform, we can always go to the student resources. It's going to give us some manuals and guides of how to navigate around the platform. And more importantly, what it gives us with our physics subscription is it gives us access to the lesson guide. And the lesson guide outlines recommended readings and labs to learn or teach specific topics. So when we jump in here, we can kind of look, so like this is basic accelerator theory for medical physics students. And so if I wanted to learn electron beams, it would tell me these are the topics I would need to read, and these are the labs I would need to do, and that would give me a good background of the topic of electron beams. And so for PDD dosimetry, we can kind of go down to our quality assurance of linear accelerators for medical physics residents. That seems like probably a good place to start. And we can maybe find the beam dosimetry and PRF lessons because they're going to cover topics like photon beam characteristics, flattening, beam flattening and energy dependence, beam symmetry, beam quality, all these things that, are going to influence the shape and characteristics of PDDs. And so just to show you what that would look like on the site, is it's kind of telling me to go to this topic, read these chapters, and then do lab 21 and maybe jump on our TG51 simulator. So let's just go see what that would look like. So I would jump over to my course space here. And so I have my Linac operation theory textbook, and I would find my beam dosimetry and PRF. And then I would just read these chapters. So this is a great topic on ion chambers in medical Linacs, talking about, how the ion chambers are collecting dose and then how we read that dose. And then we get into some topics on Linac calibration. We have some good diagrams teaching us about the setups and things. This is really good. And now I do my quiz, do some multiple choice questions on a quiz. Talking about ion chamber segments, can be kind and monitor the entire beam. And so like that's going to be, true. And so then I would get some theory behind myself. And then I'd go back to my curriculum. It kind of tells me to go to lab 21. So I would go back to my course space. I would find my labs here. And I would find lab 21. And look at this, relative output factor and profile dependence on field size. That sounds exactly what we're trying to learn. So now it's going to take me through a set of questions, and it's going to get me to really just these labs, they isolate our simulator in one or two parameters, and then we adjust them and see the output in real time. And so now, this is a great starting point for me to learn some PDD dosimetry and understanding how our outputs are going to be changing. And kind of the last place we can go is we also have the physics QA resource, which includes some more clinically relevant topics like water tank measurements and how to interpret water tank scan data and things like that. So, we've now kind of jumped around and we have a good theoretical background, and now we're kind of ready to jump over to the simulator and explore these principles directly with more of a hands-on like experience. And so what we'll do is we'll head over to our simulator. And so our simulator is found in SIMAC here. And so we have a couple different simulators. So we have our original one, which is very limited in features. Our main one is SIMAC 2, which is the one I'll be using today. We also have a TG51 simulator, which I'm offering some workshops right now on this, taking through a full protocol. And I'll talk a little bit more about that at the end. And then now you can even see we have SIMAC 3 is coming down the line. This is a sneak preview for anybody in the webinar today. This actually just got added to the tab today. So SIMAC 3 is on its way. But I'm not going to dive into that today. You'll have to wait for another webinar on that one. And today we're going to dive into SIMAC 2. And the first things I just want to kind of show you guys, how we would set up a beam. And then we're going to go and investigate a bunch of PDDs with a bunch of different setups and look at some PDD dosimetry. So first things first is we come to our simulator, and what we can do is we can pick our machine type. So we have our Klystron standing wave, or our your variant type Linac, and your Magnetron traveling wave, or your Electa style Linac. And so for today, I'm going to use the Electa style Linac. No preference. I usually use the variant or the Klystron, and so today I was just going to do the demonstration on the Magnetron. And so first, let's just generate a beam, and I just kind of want to show you what this looks like in generating a beam, and then what our outputs kind of look like, how the simulator kind of works. So right now we just ran a beam, and so we selected default energy, and so I'm running a 6 MV, and so I'm just going to default my value. So I'm just going to toggle between my energies really quick. So that just kind of sets all my defaults back, and I just want to run a default 6 MV. So I come down here and I hit our run simulator. And so our simulation takes about 15 seconds to run right now, just because our dose convolution is a large calculation and it takes a little bit of time. But Simac 3, we're getting down to kind of instant iterations, but that again is for another day. So we'll just kind of see what this finished running, and so we can see our outputs are, we have our dose rate, we have things like beam energy, beam current, target beam energy, target beam current. And then we have things like our flatness and symmetry profiles. We can check them out at D max and at different depths. And then, of course, we have our PDDs, and we have some fluence plots here as well. And so basically the idea is we can now change any parameters involved in the modulator, the gun, the waveguide, treatment head, and then we can rerun our beam and then see how that's going to affect our outputs. And so specifically, we're going to change our parameters and see how that affects our PDDs. So I just ran our 6 MV beam. And so I want to save that beam. This is another thing we can do with our simulator. Any beam state that we create, we can save and call back later. So I'm going to just show you how to save one, but I kind of did all the saving and stuff beforehand, so you don't just have to, sit here and watch me click run simulation all the time. So we just ran our 6 MV. So I'm just going to call that 6 MV March, what's the date today? 26th. And I'm just going to save state. And then we can see in our load state drop down that my 6 MV March 26 beam is there. And so, if I were to change to a 15 MV beam, we have a different bending magnetic current. And then I were just to pull up my 6 MV March 26, we can see my energy changed, my bending magnetic current changed, and any parameters that I had set are remembered and reloaded in with this beam. So now we have a beam. What we want to do is we want to run it through our water tank scan, so that we can run all our beams through the water tank scan, and we can look at our PDDs together. So we come over to the water tank, and what we do is we would do our experiment label. So we take the same beam. So we're going to call this the 6 MV March 26th. And so then we can select our beam that we'd like to run through our scan. And so that's going to be our 6 MV March 26th. And so we can kind of confirm that with our 6 MV. We're running a 40 by 40 field, which is fine. We can run, it doesn't really matter which field we run for this. And then we're going to run a depth scan. And then so we're going to run our experiment, and then we'll be able to compare over in the compare tab. And so we can see that this is running and calculating, and then once it finishes, it throws up a green bar. And so this is just kind of the first little bit. I just wanted to show you guys how we kind of run beams, set beams up, how we can save beams, and then how we can kind of run them through the water, our water tank, so we can compare them on the same graph. And so, if I went over here, now we have my 6 MV March 26 displaying my PDD. We can look at our dose 10, dose 20, and our D10 over D20. It reflects our field size and our D max depth. We can also normalize this data, and then we can see that, our dose at D10 is now normalized and is not showing a real dose. Okay, so now let's really get into the comparing and looking at some PDD dosimetry. So the first demonstration I want to show is looking at comparing two different energies, and then let's look at the PDD and what's going to happen here. So in order for us to run a different energy, all we would do is we would come back here, we would select our 10 MV, we would run it, save it, and then upload it in the water tank again, right? And that's exactly what we would do. It would be a very simple process, but I've already kind of done that, so we can just go to the water tank and we can look at the comparison here. So now I've done my 6 MV, and I'll put the one we ran today, and then I'll put our 10 MV with it as well. So you can see that the blue line is our 10 MV and the orange line is our 6 MV. And so really what we're seeing here, we can see that the overall PDD shape is similar, but there are some important differences. That the 10 MV has a higher dose in every depth. And so really what we're seeing as the photon, really what we're seeing when we upload now a 10 MV beam, we're contributing more high energy photons. So the photon beam energy is increasing, or the average photons that make up your dose have a higher average beam energy. And so as that photon energy increases, our PDD becomes higher at greater depths because the beam is more penetrating, obviously, right? As we're seeing that higher dose. And then higher energy photons, they also generate more energetic secondary electrons, which travel further into the tissue before depositing their energy. And so that's why we see a further buildup region and a deeper D max, because they're traveling in further before they're depositing that energy. And so then this, of course, shifts the dose deposition deeper, like I said, increasing our D max, and reduces the attenuation with depth, resulting in a slower fall off as well. And so that's very hard to see here in the slower fall off, but if we normalize, then we can kind of see them together. And you could maybe just see that this is going to kind of fall off a little bit quicker than it is in the blue. The blue is going to kind of start to plateau out a little bit, where the orange is going to keep going at a steeper slope. Okay, great. So now that's kind of our comparison of our PDDs at different energies. So obviously we saw we expected a higher energy, our higher dose from our higher energy. Perfect. Okay, so now let's move on to field size comparison. So now I want to see how field size affects one energy. Like I'm going to run just a 6 MV at 3 different field sizes. We're going to do a 10 by 10, a 20 by 20, and a 40 by 40. And we're going to see how our PDD changes with those different field sizes. And so how we would do that, sorry, I just need a drink. How we would do that is we would actually need to go to the treatment head. And so we would ensure, so we're on our 10 MV, so we would switch to our 6 MV. We'd like to use our 6 MV. And then we would come down to our X1, X2, Y1, Y2, and we would just change these values. So for a 10 by 10, I would just, input 5 for all of these values, and that would get me a 10 by 10 field. And right, so I would probably, name it 6 MV, 10 by 10, and I could run that beam. And then I could just change this, and I could do, 10s would give me the 20 by 20, and 20 would give me 40 by 40. And so I've already run all those, and then I've already run them through the water tank as well. And so then we'll see that the field size is also reflected, and then we can kind of look at these PDDs as well. So we'll come over here, and so I have my 10 by 10, my 20 by 20, and my 40 by 40. And so you can see the field size is reflected down here, so we are running with the correct field size, and our D max is still roughly around the same. I think that might be kind of displaying a little bit wrong. It's kind of showing that it's a little bit. Oh no, it would be around. Sorry, I'm not thinking straight. On the 6 MV, it is definitely the same. And then we're looking at our dose 10, dose 20, and D10 over D20 as well. And so what we can see here is as the field size increases, we're getting a little bit more dose, right? And what's contributing to that is more scatter radiation is generated within both the patient and the Linac head, which contributes additional dose at greater depths, right? Because basically if you think about our field as like a hallway, we've made our hallway bigger, which allows for more interactions and more scatter is introduced. But then we can also see that it's not a total linear relationship, that as we went from our 10 by 10 to our 20 by 20 was a bigger change in dose than our 20 by 20 to our 40 by 40, which is what we'd expect as well, because scattered contributions are contribute heavier closer to the central axis. So as we're moving further away, it's less of effective scatter addition. So we're seeing less additional dose with that 40 by 40 compared to the 20 by 20 from the 10 by 10. Okay, yeah, so that's kind of our field size comparison. So very simple there. We can see that we are getting a little bit more dose with our field size, exactly as we would expect. Okay, so for the next test, I want to do flattening filter free versus a flattened beam and kind of look at our PDD curves for that. And so again, we would go back to the treatment head. That's where the settings are for our flattening filter free. And I would just kind of ensure I'm on my 6MV. I would probably want, back to my defaults. So then you can see my jaw sizes reset back to defaults. And then I have my flattening filter free flag here. And so to run my flattening filter free one, I would just kind of select that. And then we can run our simulator. I'll just kind of show you, I'll show our cross plane profile come out. You'll see that it's, there was no beam hardening because there was no flattening filter. So it's very peaked in the center. And so that's exactly what we were kind of expecting. And so then again, we can save that beam, run it through the water tank, which I've already done for you guys. And then we can compare those PDDs on the same plot. So I have my 6MVFF and 6MVFFF. And again, we can see quite a large difference in this one with quite a large dose difference between our flattening filter free and our flattened beam. So the difference really is that our flattening filtered beam has passed through a flattening filter, which absorbs a large portion of the forward-directed photons to make the beam more uniform across the field. So we can see it's a much more uniform slope on our blue line or our flattened beam. And so, of course, this reduces the central axis intensity. So you can also see a lower peak dose and a smoother buildup. In contrast, the flattening filter free beam has no filter, so it retains its natural forward peak distribution, resulting in much higher dose near the surface and at Dmax. The difference occurs because removing the filter eliminates attenuation and head scatter, allowing more photons to reach the patient directly along that center axis, which, I think we understand that our flattening filter is going to, flatten our beam and take away a lot of the photon energy. It's going to harden that beam a lot. And if we don't have that flattening filter, we're going to get much higher dose. And that's when we see for things like, electron treatments. Great. Okay, so that's our flattening filter free versus our flattening filter beam. And that's how we would kind of investigate that relationship. And so then the very last one I want to do is changing the SSD. And so I want to show the difference of our PDDs at an SSD of 90, an SSD of 100, and an SSD of 110. Unfortunately, our SSD is not actually a part of our beam state. So I had to kind of do this a little bit manually, but I do also want to show you guys this that is available with our simulator and how we can kind of actually dive even deeper into a bit of our plots, into some of our plots. So first of all, I'll show you where I would change my SSD. It's right here in the treatment head, which makes a lot of sense. And so all I would do is I would, just change that to 90 and I could rerun it. We would kind of expect, some higher dose with a lower SSD as we're just kind of bringing that patient up, but we'll investigate that. And so really I've plotted the data in Excel, and the way I've gotten this data is we also have the PDD here when we run it in the machine config is what we call this section, and we can actually export this data. And so I'll export this and I'll show you what it looks like. But it's the data, it's the actual PDD graph data. So it's showing me the depth and the dose percentage. So it's a normalized plot, but it's showing me at what depth and what dose percentage we're getting. So that's how you can recreate your own PDDs and how you can, we have this data so you can do things like get people to calculate ROFs, and I said ROIs, but output factors and things like that. We can actually get values from our simulator to actually plug in and do some math and things like that, or calculating TMRs or things like that. We can actually get the data out to make those calculations. And so I went ahead and I did my 3 SSDs and I exported my data, and then I went in ahead and I brought it into Excel and I plotted them together. And so we can see some discrepancies in our PDDs. So we can see the blue one is a SSD of 90, the orange is SSD of 100, and the green is an SSD of 110. And so looking at the plots, we can really see the overall shape remains the same, but the dose at deeper depths increases slightly with increasing SSD. And this occurs because at larger SSDs, the beam is less divergent over the phantom, reducing the relative effects of the inverse square law with depth, right? As we go down into the water tank. And as a result, the dose falls off more slowly, leading to a slightly higher PDD values at greater depths compared to shorter SSDs. And this is just a normalized one. What you would end up actually seeing in the non-normalized one would be the fall off happens a little bit faster when you're closer, but you would see that there would be a little bit of a higher dose in the actual delivered dose for a closer SSD. Because so say if I were to run my 90 SSD, we'll run this. Oh, we might still be flattening filter free. But it shouldn't matter. It'll still show us the results. And so we can come back here to our dose rate. And so we're getting an 1163 dose rate. And then if I were to put this to 100 and run the simulator, then we can go just take a peek at what the dose is going to do and see if it's going to follow our prediction or not. Yeah, and so there we go. So then we're seeing a little bit of a lower dose with a little bit of a further SSD, exactly what we'd expect, right? We're just bringing that patient or the surface to the source to surface distance is now going to be a little bit farther. But yeah, that is the demonstration I wanted to show you. I really wanted to show you that our simulators can model these things and that we can really investigate these different topics of investigating the PDD dosimetry with different machine setups in a safe, stress-free environment, any place, any time. That's really what our simulator can provide. And this is the kind of exploration that highlights how simulations can make beam physics concepts much easier to visualize and understand for students and for experienced clinical physicists. And okay, so yeah, that's the demonstration for today. But before we wrap up, I want to remind everybody that we can get these simulations. You can get access to these simulators yourself. And so I do want to show you guys a little bit. So of course, like I mentioned before, we have our free account. We have free simulators. You just need to create an account and you get 5 free beams every day. Like those, every time I clicked a simulation was 1 beam, and you can run 5 beams and investigate 5 beams every single day with a free account. I do want to talk to you a little bit about our product offering that we have. It might be a little bit confusing. You can always reach out and we are more than happy to give you demonstrations and talk about it. But what we offer is we offer a physics package and we offer 2 service courses. Our our physics package is really a subscription to our entire platform. Gives you access to the simulators, our textbooks, our labs, everything that we have. And often programs, resident and graduate programs, purchase that subscription to provide training materials for their instructors and study materials for their students. And then on the other side of things, we have our 2 service courses. Our beginner service course is self-directed. There's no instructor, and it gives you an introduction to linear accelerators and the service engineer role in the clinic. And then our advanced course is actually a 3-month course with an instructor that gives you the advanced troubleshooting and maintenance concepts and skills to service both variant and elective machines. And so the prerequisites for either of these courses are really none. You really don't need to have any oncology background to start the beginner service course and then go through the advanced service course. You need a little bit of an electronics background, which I would assume most people attending would have, but no oncology background is needed, and they are completely virtual and use our simulators to give a hands-on like experience. And so if you'd like to discuss these products more, please reach out. And I did throw this in. These are some of our current physics customers right now. ECU, Varian has a residency program that uses it. Duke, Georgia Tech. We've had lots of great programs that continue to use our platform and our simulators to teach their students. And someone did ask a little bit about pricing. So for that physics subscription, these are the pricing details. So we kind of offer 2 options. We have one that's per instructor and per student. It's $400 per instructor, $750 per student, year-long access. or we have one more for a graduate level course where if you have 1 to 10 students, it's 1,500, and 10 plus students, it's 2,500, where the students get access for the semester, but the instructor gets access for the whole year. And our service courses are very much based on region, so please reach out if you'd like to know more information about our service courses. And again, so want to learn more, if you'd like service course pricing, please reach out to Karen Ann. She's very good at that. She's very good with the service engineers. She knows everything about service engineering, can help you get into a service course. If you'd like to know about the physics package, you can reach out to me, quinn@linacs.ca. If you'd like a trial of the physics package, please reach out to me. And like I said before, I'm offering TG51 workshops right now where I will take your team through a TG51 protocol. It's a great educational session and allows the team to get access and try out our simulators to see if it might be a good fit for your team. So thank you guys so much for joining me today. I really enjoy doing these webinars for you guys. If there's any topics you guys would like to hang around and discuss, I'm more than happy to answer any questions, hang around for discussions. But if not, have a great day. And I'm going to email everybody a link to the recording either tomorrow or by Monday. So you'll also get a recording to this. So please share around, and please, like I said, stay subscribed and follow us on LinkedIn. And we hope to see you at the next one. We really appreciate you guys joining us today. So I'll leave it. I'll open it up now, and I'm gonna leave this up just so you can see the emails and things. We had some note takers. And there's Emilio. Hey, Emilio. Glad you were able to join. Okay, great. Yeah, so I mean, feel free to go ahead and leave. We're done with the demonstration, or feel free to ask any questions. I'm gonna hang out for a few minutes for discussion. Yeah, go ahead, Doctor. Oh, maybe that was just an accident raising your hand. If you'd like to speak, just I believe, maybe I don't, maybe I have turned the settings off for that, but I believe you can unmute yourself and just speak. I think I gave that ability for the participants. Okay, well, it seems like yeah, thanks. No problem, guys. Thank you so much for joining us. I really appreciate it. I really love giving these demonstrations and hope I can continue to. So hopefully we will see you at the next one. Okay, I'm gonna go ahead and end this event. So everybody have a great day, and we will see you guys soon.